Hello there, ATS EVS 533 students. Dr. John Schrage here, helping you prepare for the upcoming third exam. Now, if you look back, actually, you'll see that there were only a handful of lectures in this exam, but that's kind of by design. In contrast to the material that we saw in the first two modules of the course, this should probably have been all completely new to most people, more or less all, actually, of the students in this class. Maybe if you took the 105 class, you've seen some of this before. But by and large, all of this was kind of new territory. And I'm okay with the fact that we had fewer lectures in this module, that we took our time a little bit. So let's kind of go through and see what kind of things are going to be on this upcoming exam. Now, you remember we started with another example of one where we pulled slides and presentations and so on from the 100 level version of the course. And once again, those are all ideas that I want you to know and I want to be able to quiz you on and so on. On the other hand, because it was less familiar to you, a lot of the stuff that was in there that turned out to be most important to this module, we ended up talking about again. Those 100 level lectures kind of just established the context of that and set up the nature of the problems and so on. So as a consequence, a lot of that kind of stuff we ended up having to kind of talk about a second time. Like, for example, we actually had to talk in more detail about numerical models, because that's the only kind of model we're using in this module. We're not talking about physical models. We didn't make a ball of gas to test to model climate change or something like that. We aren't using statistical models, past climate change to try to predict future climate change or something. It's all numerical models that are based on the equations that describe the physics of the atmosphere. In fact, you might remember that that's called the 7 primitive equations. There are 7 equations that are awful, but together they describe changes in the Earth's atmosphere. And we use those models a couple of different ways. We can talk about a numerical weather prediction model, or NWP, where that is a prediction of just like the weather in the next couple of days. Or we can use those equations in a similar way, but run the model out for 100 years to be making climate forecasts. And all of those model simulations had comparable issues associated with things like vocabulary words like resolution and the domain of the model, and how there's a trade-off between the resolution and the domain of the model, and why, therefore, like in the context of numerical weather prediction, we might have to get excited about things like, is it a regional model or is it a global model, for example. Now, in the case of climate, that doesn't turn out to be so much of an issue because, well, all climate models are numerical models of the atmosphere that are global. And in general, they have a resolution on the order of maybe a few tens of kilometers. Just a minute. Excuse me. Alright, we can do model experiments where we would run the model twice. One would be like a control run of the model, and one could be an experiment run where we have made some change to the model, like maybe change the boundary conditions or so on. And certainly the scientific literature is full of these kinds of modeling experiments, where we just run one model 2 times, one under some kind of control conditions, one under some kind of experiment conditions, and we look at those differences. That is certainly an important thing in science. And that's in general how science conducts experiments, but we're talking more specifically about how we understand climate change. And generally speaking, in the context of climate change and these IPCC reports and so on, these kind of controlled experiments like this are not really the way we tend to do such things. But we'll come back to how we structure those kinds of ensemble forecasts in just a little bit. I want to take apart this idea. Remember, we spent actually several slides, both in the 100 level stuff and in our lecture 1A, about that straw man argument of why should we trust the models to tell us something important about climate 100 years from now if we can't trust numerical weather prediction 5 days from now necessarily. And we talked about the fact that that's a very different kind of question, that has very different kinds of answers as to what we expect, and how they are different kinds of problems from the point of view of like the theory of mathematics. One is a set of problems that we call initial condition problems. That's the numerical weather prediction problems. And the other are the boundary condition problems that are about what we do in climate studies. Make sure you understand the difference between these two. Numerical weather prediction is an initial condition problem. You have to have a more or less infinitely precise description of the current conditions in order then to iterate the model forward using those as the input initial conditions to make meaningful forecasts. And the forecasts will be fine 12 hours out, 24 hours out, typically maybe even 36, 48. But after a while, the forecast gets less and less accurate until a week out into the forecast has really no value at all from the point of view of numerical weather prediction. That's in contrast to boundary condition problems, which are the kind of problems where we're talking about factors like carbon dioxide concentration in the atmosphere, the albedo of the ice sheet, concentrations of mineral dust in the atmosphere, things that don't really make a difference to like day-to-day weather. When they made the forecast of what the weather was doing today, they did not worry about what the aerosol content of the atmosphere was. That was not going to change what time that cold front came through today. But it will change things like what will be the global mean temperature 100 years from now. So we have two very different kinds of problems, and again, like PhD mathematicians pick all this apart and really get excited about the difference. This is a broader issue in mathematics. And we, both in the 100 level lectures and in that lecture 1A, talked about that in more detail. We also talked about the fact that we're going to be using this ensemble modeling strategy. And that's in many ways better than the deterministic modeling strategy, where you're running just a single model, maybe under different conditions like a control run and an experiment run, but it's just the same model. Because when you do that kind of experiment, the problem is the result that you're getting is to some extent a function of the model that you chose, right? If the climate, let's say you're choosing to use the ECMWF reanalysis version 1 model, okay, that's just the name of one of these models, the climate models that are run, and you run the model to make some kind of forecast, whether that is a forecast of the climate or that's a forecast of tomorrow's weather, but to some extent the forecast that you're getting depends on the model that you chose. That one model determined what your forecast would be. That's way less ideal than ensemble modeling, where you use a lot of models. Maybe there are a lot of different models in the sense of like they were written by different teams, they have different resolutions, they have different domains maybe. Or maybe it's the same software but run with slightly different boundary conditions or slightly different initial conditions or whatever. But you have a collection, an ensemble of these models, each of which is a member of that ensemble. And together they give you a sense of the range of possible outcomes. You don't just have one model and you're saying that that is deterministically defining what the future condition is. You're saying that this ensemble of forecasts, we are making some sense of like how we know about what's going on in the future. So now, like, we use ensemble modeling in both numerical weather prediction and in climate forecasting. Now, in numerical weather prediction, our ensembles are generally the same model run many times with slightly different initial conditions. Because the initial conditions that we get from observation stations and so on are imperfect, we could try just randomly slightly different versions of the initial conditions that are all more or less equivalent but will result in slightly different forecasts. Or we can do it in climate modeling, where we're usually using the same boundary conditions and initial conditions and running 42 different versions of the model written by 42 different research teams. Now, that can be our strategy with regard to boundary conditions, by the way, or we can actually be running the same model with multiple different boundary conditions. That's another way to do it. Although it turns out the climate is not terribly sensitive to small changes in the boundary condition. We don't get a radically different forecast of the future if we say that the peak carbon dioxide concentrations are going to be 500 parts per million than if we say the peak carbon dioxide concentrations are going to be 505 parts per million. Okay? Whereas we get a very different forecast of the future if we use slightly different in numerical weather prediction to predict tomorrow's high. If we make slight bad observations of the current moisture or the current temperature or whatever, we can get a disastrous forecast of the next couple days. We talked about spaghetti charts, remember, and how we can use them to visualize how the different members of the ensemble are acting. And how, like, in this case, we were just using two contours that are on each of the, whatever there was, I think this was 21 different versions, 21 different forecasts. And like in this case, we had some pretty good consensus between the different versions of the model as to what was going on. See how they all have contours that look basically the same, whereas sometimes they're all different, and they were all crazy like a pile of spaghetti, in which case the models are in great disagreement. There's a wide range of different things that could happen based on the current conditions. We then later looked at ensembles of climate simulations, and in general, we didn't use spaghetti diagrams. That doesn't tend to be the way climate science is done, but we tended to have things like error bars around our predictions of the global mean temperature in the year 2100. And those error bars were defined not as in like there was an error in the forecast, but as in like we had a range between the coolest and the warmest version of the model. Okay. We had other ways of visualizing the ranges and so on that we reached based on the ensemble. But we'll be seeing that in a future slide here. So what we needed to do if we were going to do climate modeling is we needed to have some set of boundary conditions that we could use to drive the models. The climate models are going to be mostly depending on what we choose for the boundary conditions. Things like the solar flux, the methane concentration, carbon dioxide concentration, aerosols in the atmosphere, stuff like that. Albedo of the surface of the earth, stuff like that. And that all comes to us from a very interdisciplinary view of sciences. And we get things like I just said here, like the albedo of the earth, the solar output, greenhouse gas concentrations, and so on. They're going to be necessary to drive the models. Now, because modeling is so computer intensive, when you run a single climate model for a 100-year simulation, that might take weeks to months for the supercomputer to do that. In general, to make that process more efficient, the IPCC coordinated to create standard sets of these boundary conditions under different assumptions. This was the so-called SRES scenarios. I think that was at the Special Report on Emission Scenarios. And this has actually been around for quite a while. These SRES scenarios were defined, I don't know, late 90s, early 2000s, something like that. But we brought together interdisciplinary teams of sociologists, climatologists, oceanographers, economists, and futurists, and so on, to come up with different possibilities of how the future could play out, and then make informed estimates as to what the methane concentration would be, or the carbon dioxide concentration, or whatever. Those kinds of forecasts generally came from equations like the IPAT relationship. Now, I know people who take this class often already have had information about the IPAT relation in other courses, so we didn't just spend enormous amounts of time on this. You've got other places in your environmental science curriculum where you can learn about this in more detail. But remember, I, which was the emission of greenhouse gases per year, was a function of population, affluence, and technology. And we had these estimates of what the future could hold for population. And in fact, there could be wild differences in the amount of people that could be living on the planet Earth in the year 2100, depending on things like social justice and war and environmental quality and distribution of wealth and so on. There could be a very large range of possible populations of the Earth. We talked about affluence, like not as in like, I don't know how many diamonds and pearls you have, but as in like how many dollars we consume of goods per person. And so, well, that's something that tends to only be going up, right? And that's not a bad thing. That is a social justice thing. That is I mean, we're not unhappy that the affluence of the world is increasing. And the affluence, too, is affected by all these kinds of factors that I have listed on this slide from Lecture 3B. Things like education, rights of women, social justice, international security and peace, rule of law, fair trade, all that kind of good stuff. Complicated interdisciplinary things to try to come up with some kind of estimate as to what's going to happen. Then there was this whole business of technology. Now, this wasn't necessarily as in beep, boop, boop, cell phones and stuff like that. This could be things like how efficiently we can extract petroleum and other fossil fuel resources. This could be about distribution of electricity on more efficient grids. This could be the availability of solar panels and wind turbines and things like that. And this led us to three important terms: greenhouse gas intensity, carbon intensity, and energy intensity. Make sure you do have those three terms sorted out. And what I think is just really awful about the IPAT relationship is it shows us what a trap we're in. Because we can make incremental improvements to things like the carbon efficiency and the energy efficiency of our technologies, and we do. That's a good thing. But P and A only go up. And so no matter what we do with EI and CI, the energy intensity and the carbon intensity, we're multiplying it by two numbers that are only getting bigger. So it becomes, we need at some point in the future to drive our emissions to zero, and the IPAT relationship shows us that it's basically impossible to even make the number go down, much less get to zero. we can't even slow down the rate at which this is increasing. That's a real problem. But using models like, well, this is a model in the conceptual model kind of sense of the word, like IPAT relationship. Using conceptual models like the IPAT relationship, the SRES, the Special Report on Emission Scenarios, created a collection of these so-called SRES scenarios that are standard. You can actually look them up in that IPCC report. They actually have tables that show, for each year of the model simulation, in the A1 scenario, in the A1B scenario, and so on, what was the carbon dioxide concentration, what was the albedo of the Earth, and so on. And you do need to know about those scenarios. The four that are kind of the obvious, they're actually called families of scenarios, but that's not the terminology. Formally, the SRES has slight differences between what they call a scenario and a family of scenarios and so on. I don't care. Okay, that's not really even standard terminology outside of the SRES. You do also, though, need to know about A1FI and A1B. A1B is the so-called business as usual scenario, which is, we eventually run out of fossil fuels. And A1FI is, no, we don't. We keep getting better and better at extracting them. Anyway, you do need to know the difference between the scenarios. You do need to know the difference between A's and B's. You do need to know the difference between the 1s and the 2s. I think you probably can sort those kind of things out, though. And then you start looking at, like, what were the carbon dioxide concentrations in the atmosphere in these different scenarios. And you can see, I'm sorry, these are the emissions, rather. This is not the amount of carbon dioxide. This is just the amount we emit each year. And you can see that different emission scenarios have a wide range of possible rates of emission, with B1 turning out to be the most optimistic and A1FI being the least optimistic. And you can then say that from the models we can actually determine things like the radiative forcing that these greenhouse gases are exerting on the climate of the Earth, and you end up with something like 4 to 8 watts per square meter, depending on how optimistic of a scenario you're talking about. Keep in mind that back in the second module of the course, we learned that at the present time, the net radiative forcing on the Earth's climate is like, 0.6 to 0.9 watts per square meter. So this is a huge climate forcing by the end of the 21st century. And it turns out that most of that climate forcing is being done by carbon dioxide in the atmosphere, so that is by far the most important factor that we can control. And you can kind of see, if you actually extend this forward and actually run the models to see what the amount of warming is, you can see that there's a realistic range of possible temperatures. The planet is not going to warm by 20 degrees Celsius between now and the end of the 21st century. And it's not going to warm by 0 degrees Celsius or half a degree Celsius. A good range is somewhere around 2 to 4 degrees Celsius. A little bit more, a little bit less, depending on what scenario you're on. I apologize about that. I was expecting an important phone call and couldn't get rid of my phone despite the fact that I needed to be recording this review. Anyway, I apologize. You shouldn't have to hear that. Anyway, another thing that you should be able to see on these figures from Lecture 3B, though, is committed warming. That pink curve on there is if we just held the concentrations in the atmosphere of carbon dioxide and methane and so on constant. How realistic that is and so on, that's another story. But notice how the temperature keeps creeping up just due to the committed warming. Again, that's an important vocabulary word to know really throughout the course. But all those scenarios and so on, we tend to only extend the model simulations out to about 2100, maybe a little bit farther, because beyond that it gets really hard to develop the boundary conditions. Oh, we can certainly run the model farther. I mean, there are simulations that we do in like paleoclimate studies and so on where we take it much farther than this. The model's not the problem. The problem is we don't really have a meaningful idea of what the boundary conditions are going to be. Do we really have any sense as to what carbon dioxide concentrations in the atmosphere are going to be, or what land use is going to be like, or something like that? There's not really a way to meaningfully make the boundary conditions to simulate these future climates. But there are ways to do just sort of simple models to get a sense of, well, what would happen if we just said no more emissions? Well, it kind of depends on when we stopped having emissions. And that was what this paper that we talked about in that lecture 3B was all about. We're like, what if we stopped emitting at 450 parts per million? What if we stopped emitting at 850 parts per million of carbon dioxide? And so, I mean, our boundary conditions are kind of easier to define then, right? I mean, they're basically just, and then from then on, well, wait a minute. Why are our carbon dioxide concentrations in that top panel tailing off after that? Well, it's about the carbon cycle, right? The model can correctly understand that carbon is going to be moving out of the atmosphere and into other reservoirs of the carbon cycle, like the land biosphere or the ocean's mixed layer, and so on. Okay, but that's kind of a slow process. It's a fairly fast process if you look at the slope of those lines. At first, it's a pretty fast process, but after a few decades, it kind of just becomes a very, very slow process of returning that carbon dioxide, transferring that carbon into other reservoirs. It just doesn't happen all that fast. That was kind of our first hint about this idea of irreversibility. We'll talk more about that later. But, you know, you get these climate warmings. I mean, like I highlighted it on this panel from that paper. What happens at the climate if we peak at 850 parts per million of carbon dioxide? And you see that we basically get stuck at about 3 degrees Celsius of climate change in that case. And I mean, 1,000 years from now, they're still dealing with a 3-degree temperature difference compared to pre-industrial levels. That's where we use this word irreversibility. I mean, yes, on geologic timescales, tens of thousands of years from now, all this carbon will have been soaked up by other reservoirs in the carbon cycle. But it takes vastly longer for the carbon to be removed from the atmosphere than it took to put it in there and for it to cause the climate change. That's what we are talking about here when we talk about this reservoir of carbon, about this irreversibility. Now, after spending a bunch of time talking about these SRES scenarios like A1, B1, A2, B2, I then broke you the news that actually that's kind of a terminology that's a bit falling out of favor. I don't want to say that it's the end of the world. It's just that that's kind of not the direction in the long run climate's going. But don't get me wrong, textbooks and papers are going to be using that kind of terminology for the next couple decades. I mean, that's such a standard thing now. But this turns out that these scenarios are not so easy to compare to each other when you compare one model to another. If you ran Model 1 and with the A1 scenario, and you ran Model 2 with the A1 scenario, they should in fact be the same. Well, not the same as in their forecast. The radiative forcings being exerted on the climate should be the same. But it turns out they're not quite the same, because each of the models has its own carbon cycle in it as part of its system of equations that are driving the Earth-atmosphere system. And they aren't exactly the same. So even though you are specifying, you know, how much carbon there is in, you know, at each year of the model run, as the model simulation runs, different models are actually better or worse at moving the carbon from one reservoir to another and so on. And it turns out that there's kind of a theoretical problem here. These model runs are not that easy to compare to each other. Which is why there's this new RCP way of describing how we could drive models using the boundary conditions, where you're saying, it does not make a difference to the model whether the warming is happening due to carbon dioxide or methane or black carbon or whatever. So rather than sit there and try to use these complicated ideas about the future of where we're going to talk about all these interdisciplinary things about economics and population and so on, all trying to come up with an estimate of methane and then to come up with an estimate of carbon, here's an idea. Let's just specify how many watts per square meter of radiative forcing there is, and we just don't care how it happened. I really don't care if it's because of increased growth of the fossil fuel industry, or if it's due to distribution of green technologies. I don't care. Okay? So we instead just specify, these are the so-called representative concentration pathways, or RCP scenarios, where we just say there's going to be a certain number of watts per square meter of radiative forcing due to anthropogenic factors, like 2.6 watts per square meter, or 6 watts per square meter. That's what those numbers mean. And that way, we're not trying to come up with these complicated ideas about social justice in the future and so on. We're just saying, I'm comparing these possibilities. What if there's this much radiative forcing? What if there's that much radiative forcing? And so on. And from that information, we can retrieve back, there's mathematical ways to get back, well, what would be the carbon dioxide it takes to make that happen? Or what is the amount of methane in the atmosphere it takes to make that happen? And so on. But that's not fundamental to how the model works. The model is actually just using the radiative forcing. It's just from a philosophy of modeling kind of perspective, that's actually a better idea. And so we can use these RCP pathways then to, again, pathway, scenario, family of scenarios, all this terminology is that kind of stuff. I don't get bogged down in that, okay? We can use these RCP pathways, though, to start making very easily compared apples-to-apples type forecasts of what the near-term climate is going to be. And by near term, we mean between now and the middle of the 21st century. Well, you can start looking at like what the temperature is going to be. And you can see that we have some scenarios as we move forward, like this happens to be RCP 4.5, where we had 42 different model runs. We're all using 4.5 watts per square meter of radiative forcing due to anthropogenic torus sources. And you can see as you go out to like the year 2050, there's a range. But they're all trending upward. I don't think the mean is on here, but it looks like the mean is about a total of about 1.5 degrees Celsius of climate change and so on. You get a sense, though, of, it could be as high as like 2 degrees Celsius. It could be as little as like maybe 3/4 of a degree Celsius, something like that. This is another way of visualizing what we are getting from our ensemble. All right? Probably not a huge surprise based on the things that we learned in Module 1, where we saw that most of the warming that's happened so far has been in the Arctic due to ice albedo feedbacks, right? As the ice melts, the surface of the Earth is exposed, it absorbs more shortwave radiation. In the same way, between now and the middle of the 21st century, we expect most of the warming to happen in the Arctic. And the stippling, as you might recall on that diagram there, is where there is the greatest consensus between all 42 members of the model run. This happens to be, I think, 4.5, I'm not sure, yes, RCP 4.5. And so in all those model runs, we saw warming. That's what the stippling means on there. It's another way of expressing what we're learning from the model ensembles. The average is what's colored on there, but the uncertainty associated with the range of them and so on is indicated by the stippling. We are quite confident then that the world is going to be getting warmer, as you can see there. And as you can see, we also have great confidence that most of the warming is going to be happening over land, with less of it happening over the ocean. A strong result based on like the physics of how oceans warm and the higher specific heat of the ocean and the mixing of the ocean and so on. So we're going to see bigger temperature changes over land in the different scenarios than we do over the ocean. That has consequences, as you saw later in this module, for like monsoons of the future. We learned that warm days that are warmer than 90% of the time on that same calendar day of the year will become vastly more common in the 21st century. And again, the uncertainty is expressed by, again, this kind of error bar, not uncertainty, the range of the range of outcomes that we saw in the 42 different members of the ensemble. You can see all of the models agree that there's going to be an increase in the number of warm days, and not all that surprisingly, there is a decrease in the number of cold days. I mean, sometimes people think there'll be more cold days and more warm days, but that's not the way it works at all. In fact, we're going to be having practically no cold days anymore. We learned that we're expecting, well, it becomes more complicated, but we're expecting in general a warmer world to be a more moist world with more precipitation and so on. But remember, the cross-hatching on these diagrams means that we have very low confidence in the results. Some of the models showed increases in precipitation, some of the models showed decrease in precipitation over each of these regions. Exactly where on the Earth there'll be more rain and where there'll be less is not that clear, at least, as in on a map. Okay, like every individual location, is there more rain or is there less rain? We just don't have that much confidence in that. On the other hand, well, we have some confidence that there's going to be more evaporation, which makes sense. I mean, the evaporation rates are determined by the Clausius-Clapeyron equation, which itself is the temperature, right? The more warmer the water is and the warmer the air is, the more evaporation there should be happening. Okay, we don't have really high confidence in that, but certainly in some parts of the world we have good confidence there'll be more evaporation. But no matter what, we do have a good sense that overall the atmosphere will have a higher specific humidity. Now remember, specific humidity is a measure of the absolute amount of water vapor in the atmosphere. That's in difference to relative humidity, which we'll be seeing in just a little bit. But you can see that everywhere on Earth, the amount of specific humidity is going to be going up. And the stippling there tells us that it's going up by, we have great confidence in that result. All of the models agree on that. That's different than the relative humidity. You'll notice that in general, over land, the relative humidity is going to be going down, and over water, the relative humidity is going up. Now, the confidence in that isn't so great, but I like the fact that that's intellectually consistent with our understanding of relative humidity being a combination of temperature and moisture content of the atmosphere. Since the temperature is increasing so much over land, the relative humidity is actually going down. Even though there's more water vapor in the air, we're farther from saturation over land because the temperature has increased so much. So I like how that's consistent with what we saw before. in general, one of the things people are worried about is extreme precipitation events. And the models are in very good agreement. And again, notice how like those sort of error bars or the shaded regions there, all are in agreement that there will be more very wet days. Days that are wetter than 90% of the days in the past. So we have more precipitation, more extreme events, and so on. Now, to kind of dig a little deeper into this idea of how precipitation was going to be changed, we needed to actually use a set of tools called the zonal mean, zonal mean temperature, or zonal mean precipitation, or zonal mean evaporation. On this slide here, I happen to have zonal mean temperature highlighted. Make sure you understand this idea of something being the zonal mean, or being zonally averaged. That means we're taking all the values along a particular latitude line all the way around the world to get the average. So like, for example, this inset here, that's this Excel plot here, that's the zonal mean temperature at 1,000 millibars, so quite close to the surface of the Earth for a particular time of year. And I would want you to be able to interpret what you have here. I mean, notice how like from like 10 degrees south to, got latitude on the x-axis here. See how from about 10 degrees south to about 10 degrees north, we have very high temperatures, you got lower temperatures down near like 90 south and up near 90 north, and so on. Makes good sense, right? It's the average temperature along the equator, the average temperature along 10 degrees north or whatever. For that matter, we could have zonal mean cross sections. I'm not sure that I buy that I'm going to actually have the diagram like this on the test. But, you know, could you interpret this as the same plot as what we were seeing before, except instead of just being at the 1,000 millibar level and close to the surface, we now see all the layers of the troposphere. Cool. We had to learn some notation to make this work, where bar meant time average, like averaged over 30 years or something like that. But bracket meant averaged zonally. So there are two different ways of indicating an average. So like T-bar bracket would be the average value of temperature over a long period of time averaged around the world at this latitude. Okay? We needed those kind of terminology when we started talking about things like the distribution of precipitation around the world. Like, for example, this is actually the observed distribution of P-bar bracket, the precipitation averaged over a long period of time. I think this is a 30-year average, zonally, and then zonally averaged, P-bar bracket. And you can see all kinds of important features. Now, the different curves on here are just different data sets and so on. But the basic idea that there's like high precipitation down near the equator, low precipitation at about 30 degrees north and 30 degrees south where the subtropical highs are, very low precipitation near the North Pole and the South Pole, all makes good sense. It helps you interpret these kind of results that we're going to be seeing here. And you can see then that once we understand that kind of notation, we can start having maps of like what the models think is the change in precipitation, or the change in the rates of precipitation minus evaporation. And we can see that, like, for example, more or less all the models agree that there'll be more precipitation in the tropics. Delta P bracket is increasing across, like, the equator. But it is negative at, like, 30 south and 30 north. The subtropical highs are getting drier, the ITCZ and the tropics are getting wetter, and so on. Notice how much wetter the polar regions are getting. That's going to have implications for, like, the mass balance of ice sheets and so on. But as we get farther and farther into the future, we saw that these projected temperature changes get worse and worse and worse. Remember, this is for different representative concentration pathways, RCP values, farther and farther into the future. And you can see, depending on how far in the future you're willing to go, you could get a very strange climate system. And as we thought about this a little bit, we realized we kind of had another theoretical problem here. All these results that I've been talking about so far are about the atmosphere. We've been talking about atmospheric results that are simulated by the model. But the atmosphere is, in the real world, just part of the larger Earth system. Earth, atmosphere, ocean, cryosphere system. And so there could be changes in like ocean currents, ocean temperatures, ice caps, glaciation, changes in land use, vegetation coverage, and so on. And this is all really hard to make sense of, because some of these things are just physics. I mean, we could talk about like being able to use a numerical model to predict changes in the ocean, like changes in temperature, changes in currents, and so on. But it's awful hard to see how we're going to come up with some kind of model that predicts like changes in land use. You know, some kind of model that's going to predict how much cities grow or how much farmland's albedo changes. pretty hard to envision how that kind of biogeometeorological stuff is going to change. So let's focus on the stuff we could actually talk about, like the physics stuff. We talked a lot about the fact that there's such a thing as numerical models of the ocean, where we use the primitive equations that describe how ocean currents happen, that are driven by things like temperature and wind stresses at the surface of the ocean and salinity and so on. Oceanographers think they invented this stuff, right? They created these models based on their primitive equations. And there are ways to couple an ocean model to an atmospheric model to create these sort of grids that we saw in Lecture 3D, where, we could use the winds from our atmospheric model and our fluxes of heat and moisture and fresh water and so on from rain and things like that to make forecasts of what's going on in the ocean. But it could be a two-way coupling. We could also let the ocean, by its temperature and so on, have transports of heat and moisture and momentum and stuff into the atmosphere. It's a two-way coupling of these two sets of models. That isn't always necessarily the case. For simpler situations like just making forecasts of the weather for tomorrow, it might be enough to just say let the ocean affect the atmosphere. The temperatures of the ocean make changes the atmosphere because the changes the atmosphere makes to the ocean are slower. By the time these winds off the coast of North Carolina would actually produce changes in the ocean currents, they produce changes in the water temperature, well, long before that, the numerical weather prediction models actually, we're out beyond the forecast range anyway. So there are sometimes, especially in numerical weather prediction, where we don't need to have two-way coupling. But no doubt about it, all climate models have some kind of coupling of an ocean model to the atmospheric model. Now that can be wildly complicated, or that can be fairly simplistic, and there's no single right way to do it, but all the models that we're looking at in the IPCC reports have some interaction between the ocean system and the atmosphere system. But all of them show very similar things when you start looking across whether they're forecasts between now and the middle of the 21st century. And all of them, unsurprisingly, show the ocean continuing to warm. The trend that was observed in the last 100 years continues out into the middle of the 21st century. Yes, there's more warming for different representative concentration pathways. There's less warming in others, but the basic idea that all the models, again indicated by those colored bars, to kind of give a sense as to what the range of the models are, all the models agree the planet's oceans continue to warm, and in fact we can use these kind of expressions of the uncertainty and so on to show that the average warming shows us that there's warming everywhere. It isn't like the warming is concentrated in the Arctic or the Antarctic or anything. Pretty much the world's oceans are warming. And we have icy stippling, which means we have very good confidence in that. All of the coupled ocean-atmosphere models are all showing warming pretty much everywhere around the world between now and the middle of the 21st century. But of course, that's not the only way we could have a coupled model. I mean, there's more aspects to the Earth, atmosphere, ocean, climate, cryosphere system, like cryosphere. And there is such a thing as numerical models of the cryosphere, but they get to be less and less certain. Because the truth is that we don't have the greatest understanding yet of all the processes that determine the rates at which ice sheets melt versus advance versus retreat. We don't know that much about changes in permafrost. We don't know that much about the processes that determine the rates at which glaciers advance and so on. But you could make a coupled model where the atmosphere is making changes to the ice of the world, the ice, and it could in fact even theoretically be a two-way couple, although I don't know that any of the current state-of-the-art models do that. But you could in theory have it like be as glaciers retreat, they can also affect the atmosphere. Maybe there are two-way climate models that involve two-way coupling between the cryosphere and the atmosphere. I don't think there are, but maybe there are. But what do these models tell us about it? Well, the IPCC had some pretty harsh words about the cryosphere in the AR5. They basically said that there's strong reason to believe that a lot of the models are giving us reason to believe that we're going to live in a world where there's no sea ice in the Arctic in summer anyway. We're at the end of the summer when it's been melting back. In fact, plenty of models showed that first summer that's ice-free could be as early as the year 2037. And basically all the models showed it by the end of the 21st century. Oh, wow, that's some pretty scary stuff. There's all kinds of complicated climate feedbacks that could happen as sea ice retreats in such a dramatic way. We talked too about like permafrost is another example of a factor in the cryosphere that could have impacts on climate, and we'd love to be able to make some kind of numerical model of permafrost, but it turns out we don't really know that much about permafrost. There's a lot of it up there. It's a frozen soil, frozen to great depth, and it contains a whole lot of dead organic material, and as it thaws out, bacteria opportunistically come out there and start eating it and releasing carbon dioxide back into the atmosphere by their respiration. So that's a climate feedback, right? I mean, as the carbon in the permafrost, as the permafrost melts due to a warming planet, we get more carbon out of the permafrost, which results in more warming, and we'd love to be able to make some forecast of that. But the truth of the matter is we don't really understand the physics of permafrost all that well yet. And, we have insufficient understanding to know the rates at which this will happen, how reversible or irreversible it is, etc. So we have so much uncertainty about these things. What if we tried looking at the other way around? Instead of saying what's going to happen with all these doomsday scenarios, how about something happy? Like, what if we just stopped emitting having anthropogenic emissions, both greenhouse gases and things like aerosols and so on? How would this happen? It wouldn't. I don't know, zombie apocalypse or something like that, right? Okay, I mean, we're just doing something to get rid of us having any emissions or whatever. Well, what would happen, it has to do with the fact that all of these different anthropogenic pollutants stick around in the atmosphere for radically different amounts of time. I mean, the aerosols will be gone in a matter of weeks to months. By and large, they're pretty water soluble. Most of them will either sediment out just due to gravity or be washed out by precipitation. Methane, too, is photodissociated into, not photodissociated, it is oxidized into water vapor, on the scale of a few months to a few years. Certainly by 50 years in the future, there'd be basically no anthropogenic methane left. But like carbon dioxide effectively never comes back to pre-industrial levels. I mean, it only happens on the scales of like tens of thousands of years. That's why we end up with this kind of weird distribution as to what would happen to the Earth's temperature if there was a zombie apocalypse or something like that, or we all suddenly discover green power sources or something like that. We end up with this weird spike in the temperature right away because we got this factor of global dimming that's actually kind of helping us reduce the impacts of global warming. Remember, global dimming was due to like all that sulfate and stuff that we had in the atmosphere due to coal power, which astonishingly is actually kind of helping with the problem of global warming, but that stuff would all be washed out of the atmosphere in a few weeks to a few months. And as a consequence, the planet would actually warm up really fast. There'd be a quick spike in the temperature of the Earth. With time, we get past that and move, I mean, that's not the long-term scenario then, but it's actually kind of crazy that we'd actually have that temperature spike. But notice how this thought problem about what could happen to the climate of the Earth if we just stopped having emissions, more than how realistic that scenario is, it kind of pointed us to three key issues: irreversibility, commitment, and climate stabilization. Now, we have slides that are specifically like the definition of irreversibility and so on, and please do know that, and we've talked about irreversibility already here in the review sheet. We also talked about the fact that there's a commitment involved. Not as in like we're committed to doing something or whatever, but as in there's going to be some temperature even if we stopped having emissions, there's a temperature we reach just due to committed warming. And we can kind of define that. We can decide, hey, what if I'm limiting my climate change to a certain temperature? Or what if I am limiting my emissions to a certain amount? Or what if I'm limiting the amount of climate change I'm willing to tolerate in terms of dollar value? There were all these different ways we could use climate models to simulate different climate change commitment studies. There's also this business about climate stabilization and how once we reach zero emissions, the climate will eventually stabilize at some new equilibrium temperature. Now, remember the key here is though, zero emissions. The climate can't reach any kind of climate stabilization as long as the emissions are still happening. But once the emissions stop, the climate can stabilize at some new temperature here. But that's the key here. no matter what you decide you want to have as your climate target, whether that's a certain concentration of carbon dioxide you're willing to tolerate, or whether that is a certain temperature change you're willing to tolerate, or whatever, no matter what, to reach any kind of climate target and have some kind of climate stabilization, at some point you have to reach zero emissions. Oh, make sure you understand that issue as to why. Well, that kind of led us to the gloom and doom scenarios of all these interesting abrupt climate changes that we have going on out there. And, you know, as possibilities as to what could happen. And we don't even really try to simulate these things. The climate simulations that we have been talking about throughout this module have all been assuming that the West Antarctic ice sheet's sticking around, the Atlantic meridional overturning current is sticking around, that we aren't going to have a catastrophic release of methane clathates from the ocean, etc. Well, all those things could happen. And, well, they're scary. I invite you to read the verbiage about those things, like in the review sheet and so on, but there are a lot of ways in which the climate could change very abruptly. One fine day, at some particular global mean temperature, the Atlantic meridional overturning current stops. There's some uncertainty as to what that temperature is, but we're going to reach that someday, and that is an abrupt climate change in terms of how our climate system works. The West Antarctic ice sheet is probably unstable. How fast it would decompose and, what's the right word? It would collapse is the right word. How fast it would, we're talking on certainly on the order of probably centuries or something like that, but we don't know. We don't know the temperature at which that would happen and so on. And we don't have any way to validate how good or how bad our models are at predicting that kind of thing, or what a world would be like without a West Antarctic ice sheet, because we have no data to which to compare our models. We don't have any observations of a world without a West Antarctic ice sheet, and therefore we have no way of knowing if our models are any good at predicting that. Same with like collapse, catastrophic release of carbon from the from permafrost. These are the kinds of things policymakers and the public most want to know about, but these are the kinds of things we actually have the greatest uncertainty about. Global mean temperature changes, we got that under control. We know what that's going to mean. Global mean humidity changes, that's not the sexiest of things, but we know all about that. Catastrophic destruction of the West Antarctic ice sheet, that's something we really ought to know, and in fact, that's what we understand least well. Now, as we talked about these abrupt possible climate changes, one that you probably knew least about going into this was the whole business of methane clathates. These are those methane ices that exist under a particular range of temperatures and pressures that happen to be consistent with what's at the surface, at the bottom of the ocean over much of the area of the ocean. Especially at a range of like 3 to 4 kilometers below the water or something like that. And decomposing organic materials at the bottom of the ocean can result in the formation of these methane clathates. They're abundant, they're everywhere. They are the single largest set of fossil fuels on the surface of the Earth. Well, fortunately there's no meaningful hope that we'll ever exploit them for lots of reasons. That would be horrible to be dredging the ocean looking for these things and so on, but who knows? If the water got a little bit warmer, most of the deep ocean is right around 3 degrees Celsius. And it turns out you can have methane clathates at about 3 degrees Celsius. But even a little bit warmer than that, methane clathates start sublimating back into bubbles of methane that come out of the atmosphere and out of the ocean, and you release them into the atmosphere, and suddenly you have this powerful greenhouse gas bubbling back into the atmosphere. Oh, that's a catastrophe. For that matter, we could talk about like dieback of forests, a real possibility that we don't really have any way to numerically model. We don't really know anything about how likely those things happen. Well, that's a vegetation feedback, right? If the climate changes produce changes in the vegetation, and the changes in the vegetation produce a change in the climate due to release of carbon dioxide back into the atmosphere or something like that, that's a vegetation feedback. Again, we're not very good at modeling that, and we're not really very certain we know that our models of the atmosphere are very good after such a thing happens. Oh, that's not good. One climate change that certainly could happen and would affect literally 1 billion people around the Earth is changes in the monsoon system. Monsoons are fundamentally driven by the fact that in the tropics, there is a seasonal cycle to the difference between the temperature of the ocean and the temperature of the continental land masses. And we've seen already that under global warming, we're expecting that difference to increase. The continents are expected to warm more than the ocean does. But what that means for the monsoon itself is not very clear. Does that mean the monsoon will be stronger? Does that mean the monsoon will be drier? Does that mean it will be wetter? Does that mean the monsoon will progress farther north and south of the equator? Last longer, last shorter? We don't know. We really don't. There's no consensus between the models as to what that means. And only 1 billion people depend on the monsoon for their water. This is a very serious problem that we don't even have good skills for figuring out what this means. So what I'm trying to get to you here is this business of how we have all this uncertainty about some of the most important aspects of climate change. Now in the fourth module, of course, we're going to have to start thinking about how we can mitigate such things or how we can plan for such things or so on. I do want to remind you that you did have that interesting reading about the possibility of global warming and hurricanes. We can't really have a physical climatology and climate change class without talking about that debate. Now, you aren't expected to know about all the crazy statistical tests and stuff like that. Basically, if you understood it at the level of those questions that were asked about it after you did the reading, you should be fine. All right, but do let me know if you have any questions about any of that. That's a whole complicated debate. All right. You have all this stuff to help you review for the upcoming test. Please let me know if you have any questions, and good luck with the test.